Hi everyone, my name is Kingsley Doko and I want to welcome you to this section of my YouTube video on Introduction to BGP Routing Complete. In this section, we are going to be talking about the BGP scaling method, how to scale IBGP peerings. So we'll describe the BGP scaling method. We're going to talk about the full mesh topology. We'll also talk about the route reflector designs and also the confederation. When we are done with that, we're also going to talk about the BGP attributes, the categories of BGP attributes. We're going to look at the different BGP attributes and the categories they all fall into. Then we're also going to talk about how BGP does its best path selection process. Now, just like I said, there are different ways of scaling IBGP peering. Number one is the full mesh design. We also have the route reflector and the confederation. So what we're going to do now is we're going to look at each of these methods carefully and to see that each of these methods has their different, they have their advantages and their disadvantages. Some are much more flexible to implement, and some are rather more difficult to implement, and thus will require a lot of planning before we can do such implementation. Now, for the full mesh designs, which is the full mesh, uh, before we even talk about this, let's look at what the initial problem was, right? I remember we talked about the IBGP rules and the EBGP rules, and we said that when you learn routes from an IBGP pair, you cannot go ahead and advertise it to another IBGP pair. So what that means is, let's say for example, I have three routers. So this is router one, and this is router two, and this is router three. Okay, so there's a physical connectivity between these routers. So this is router 1, router 2, router 3. Okay, so the problem is this. When router 1 originate prefixes, okay, so let's say it originates a prefix called prefix X, he can go ahead and advertise it to router 2. Okay, remember the pairing here is what? IBGP. Here too is IBGP. Okay, so when he originates this prefix, he can go ahead and what? Advertise it to router 2. But the problem is router 2 cannot go ahead and advertise it to router 3. Why? Because it's a loop prevention mechanism, right? For loop prevention. Okay, so locally originated prefixes can be advertised to IBGP pairs, but route learned from other IBGP pairs cannot be advertised to another IBGP pair. That is, router 1 can advertise the route to router 2, but router 2 cannot go ahead and advertise it to router 3. The same applies for EBGP learned routes. So let's say, for example, I have a pairing with a different provider. So let's say this is an ISP. So whatever prefixes that this ISP advertises to router 1, okay, so router 1 can as well go ahead and advertise it to router 2. However, once router 2 gets it, router 2 cannot go ahead and advertise it to router 3. So in this case, it means there is no full convergence, right? Because router 3 does not know of these prefixes. But whatever router 2 originates, so if router 2 is originating prefix Y, router 2 can advertise it to router 1 and as well router 3. Okay? But router 2, if router 3 has a neighbor that is also connected through an IP that is also appearing as an IBGP pair, router 3 cannot go ahead and advertise it to that neighbor. Okay, so that creates a problem. The problem is there's no full convergence. So that is why you now have what we call this different method we can use to overcome this loop prevention issues that is associated with IBGP. So what you are going to have is this. Let me erase this. Is that if we now have three routers, okay, so router 1, router 2, router 3, router 1 is now going to form pairing with router 2. At the same time, it's also going to form a pairing with router 3. Okay, so similarly, router 2 will form pairing with router 3, right? So in that case, router 1 can directly advertise its prefix S directly to router 3, and router 2 can also advertise it to router 1 and router 2. That's the whole idea of what the full mesh design. That is, if I have four routers like this, okay, So they form what we call a full mesh design, a full mesh topology design. That is, every router is pairing with every other router within the topology. So the idea is we want to have convergence, and we also want to overcome the IBGP peering rules and also the loop prevention mechanism that is associated with IBGP. So that's what basically what the full mesh design is. It has its advantages, it has its disadvantages. One of the advantages is that, as you can see here, so one of the advantages it has is there's optimal traffic forwarding. We're going to talk about this when we actually do the implementation. There is path diversity. So one of the advantages is that there's optimal traffic forwarding, there's path diversity, there is faster convergence, and there is resilience. So the idea of optimal traffic forwarding is that uh, every router perform what we call its own calculation and determine the best path to a destination. So if I have a prefix that is being learned by this router, let's say this is router 4, say this is router 3, and this is router 2, and this is router 1. Router 1 has three ways or three best or three paths to get to this prefix X, right? So if one path fails, it still has other paths, right? So there's optimal traffic forwarding because router 1 can then choose which path is the best to get to router X. Similarly, there's path diversity because you have multi paths to get to that destination. There's also faster convergence in that if this node should fail, then I still have other ways or other paths that I can use to get to that destination. There's also robustness. There's whenever if there's a link failure, there's a node failure, it doesn't or shouldn't impact connectivity because uh, there's this path diversity within the core. Of course, when we do the implementation, you're also actually going to see it from our the implementation that the different advantages of BGP full mesh designs. But additionally, it also has its disadvantages. The disadvantage is that scalability is a major issue with full mesh designs. If you go to the real networks today, you will hardly find where there's full mesh topologies or full mesh design for BGP because of the scalability issue that is associated. I mean, with four routers now, what we have is how many pairs? How many pairs do we have here? We have one, this is two, this is three, this is four, and this is five, and this is six. So I think there's a formula called the n times n minus 1 divided by 2. So for 4 nodes, you see, we ultimately give us 6 pairing. What about for 10? So for 10, that would be 10 bracket 9 divided by 2, right? So this is going to give you 45 pairings. Okay, so that is a problem. That is a problem in that as the network starts to scale or as it starts to expand, as you are bringing in new nodes into the core of your network, then scalability becomes a problem because every node must pair with that new device you are bringing in. So that there's a lot of administrative overhead, there's management overhead, and you also see that there are duplication of informations. Okay, so we are really going to look at this later during the implementation of IBGP pairing. You are going to see much of the design disadvantages, which is I think is much talked about than the advantages of full mesh topology. Full mesh topology is very fine, is nice for a smaller environment, but when you start expanding or scaling your network, it then becomes a problem because of it's not as flexible as the other method that we are going to talk about. All right, so moving forward, uh, we also talk about Route-Reflector. With Route-Reflector, this is the most simple method or the most scalable way of implementing or scaling IBGP pairings. So with Route-Reflectors, what you have is you have, so let's say for example, let me go my pen. What you have is if I have like let's say I have this four routers, so I have router 1, router 2, router 3. Let's also say I have router 1, router 2, router 3. What's going to happen is we are going to pick one of those routers as a route reflector. Okay, so it could be a physical router, it could be a very, it doesn't have to be a physical device, but in one of the nodes we are going to make it a route reflector. So what route reflector does is that every router is going to pair with the route reflector. Okay, so yes, this pairing that goes on between the nodes and the route reflector, and then so once the pairing has been established, they then share what we call their prefixes, or they then advertise their prefixes to the route reflector. The route reflector then learns of the prefixes from all the neighbors and then advertise it to everyone. So there's no split horizon rule that says whatever I learn from here, I cannot advertise it back. So whatever the route reflector learns, is automatically advertise it to every other neighbor. So in that case, whatever all routers will know of every prefixes within the IBGP. So the pairing is IBGP. So they all pair to the route reflector, and then the route reflector then in turn advertise those prefixes to its neighbor. So for route reflectors, it's similar to your OSPF uh, designated router and your backup designated router. Remember that within a segment, all routers the router that has the highest router ID, okay? So the router that has the highest router ID becomes the designated router, and so every other routers within that segment automatically form what we call adjacency with the designated router. So and also the backup designated router. So that's the same way uh, route reflector works with BGP. The only difference is that for OSPF it happens automatically, especially when you are using the broadcast or uh, uh, when the OSPF network type is broadcast, they automatically pair with the designated router and the backup designated router. These ones are automatically uh, um, they are automatically selected, and so the pairing occurs automatically. But for route reflectors, it's something that you have to manually configure. You have to say that this is a route reflector, and so every other routers, you now configure all these other routers to pair with the route reflector. Now for route reflector, it also has its own advantages and disadvantages. Uh, the advantages is that there is there's scalability. Of course, you can add as many nodes as you want, uh, because the nodes they all just need to when you're introducing a new node, all you need to configure is to configure it to pair with the route reflector, and the route reflector can in turn uh, learn prefixes from that new node and then advertise it to other routers in the network. Then there's also reduced operational cost. The idea is you don't need to spend a lot of time scaling it all compared to your BGP full mesh designs, where you have to start configuring and requires a lot of time. There's also reduced information in the RIP. The reduced information has to do with, and we're going to talk about this later. You are going to find out that one of the major issue with route reflectors is that uh, the optimal path, there's no optimal path in the sense that the route reflector is one making the decision as to what the best path is. And that is what eventually gets advertised to its neighbors. So, unlike full mesh designs where you have full visibility into the topology, you learn prefixes from every other pair, and you're able to use your optimal path to destination, you're going to see that for route reflectors, the decision is not entirely for the node. The decision is now done by the route reflectors in making best path selection. So what eventually happened is reduced size in the BGP table for the route reflectors, because you will not have this multi-path to destinations. What you only learn from the route reflector is the best path to the destination. If that best path fails, then you have to um, do another calculation, or the route reflector will now have to advertise the different paths to that node. So there's reduced RIP size. We're going to talk about that later. There's also reduced in terms of the number of BGP updates. So the update you are getting only comes from the route reflector, uh, and so not directly from your other neighbors. There's also flexibility in terms of incremental deployment. You can add as many new nodes as you want. Providers, when they create new POPs in different regions, all they just need to do is, so long there's transport between that node and the route reflector, all they just need to do is to pair with the route reflector, and then they then advertise their prefixes, and they also are able to learn about every other prefixes that exists within the network. So route reflector also has its own disadvantages. The idea is, if you have just one route reflector and that route reflector goes down, or you lose reachability to the route reflector, it means that's going to be a lot of problem. Of course, what most providers do today is that they will have multiple route reflectors. So you can have one or two or three route reflectors, and these route reflectors in turn pair with each other, and so they're able to advertise prefixes. So every node pair with all the route reflectors. So even if one of the route reflector fails, you still have other route reflectors within your ecosystem to pair with. One of the other That's one of the disadvantages. There's less resilience, so we don't assume that you are going to lose all your two or three rod reflectors you have. But if you are using one rod reflector and then something happens, whether to the hardware or to the BGP process, that's going to cause a network outage. There's also slow routing convergence, because if you lose reachability to a particular prefix, then you don't really have that diversity or that alternatives. You have to wait for the route reflector to advertise to you a new path, a new best path to that destination. So as compared to the full mesh designs, in which you can quickly uh, uh, perform another calculation and choose the best path, here you have to wait for the route reflector to advertise a new path to that particular destination. There are also potentials for loops with route reflectors. I can't really think of a way that what might cause potential loops, but when we do the implementation, we're going to look at that too. There's reduced path diversity, because you already know that for BGP, only the best path advertised, right? So when you learn all the prefixes from all the nodes, you are going to apply your local policy to those prefixes, and only the best part goes to the routing table, which is the read. So those what ends up in the routing table are the best part. Those best parts are what eventually gets advertised to your neighbors. There's suboptimal routing, because you are not the one, the nodes are not the one calculating the best path to a particular destination. Rather, it's the route reflector that is making the decision, and then it's the route reflector that does the calculation for best path, and the best route or the best path to destination are being advertised to the neighbors. We're going to look at this in more details when we actually do the implementation. Likewise, the other method is the BGP confederations. With BGP confederations, what you really have is you start breaking what we call the autonomous system into smaller autonomous systems that are more manageable to design. So what you have with route reflectors is this. Let me bring out my pen. So let's say I have a bunch of routers that within your it could be your service provider environment or within your enterprise. So when you have these pairings, what we want to have is full convergence, right? So what you can do is you start to break up each you start to break up the network into what we call subdomains. And so each of these devices, so this could be one confederation domain, this will be another confederation domain, and this will be another confederation domain. So within this confederation domain, they do need to form what we call full mesh topology. So you can either be using full mesh, or you can also be using route reflectors. But the idea is, here you are using what we call sub-autonomous systems, sub-AS, for the pairing. But once they want to pair with other domains, then they will now need to use what we call the public autonomous systems. So in this case, there are situations whereby you are not just breaking down the BGP domain, but you're also breaking up the IGP. So here they can as well be running separate IGPs, okay, separate IGP, but they could as well be running just a single IGP within the whole uh, network. But the idea is you are creating subdomains into a more manageable domains. And so when you add a device within this domain, you only need to pair them with all the routers within this domain. So that is much more manageable or much more simpler to implement as compared to uh, the full mesh designs. Of course, confederation is rather more difficult to implement. I mean, when if you want to implement confederation, it's something that you have to start right from the start. It's not so. It requires a lot of planning because it's not so easy for you to maybe move your network from full mesh design to confederation, or from route reflector design to confederation design. I can't really think of the advantages of confederations over the others, but I can tell you that route reflectors is way much more flexible than the full mesh design. So just like we said, is you are breaking down your BGP domain into what we call smaller manageable domain. Then you can as well split up the IGP domain. There are service provider environment like your tier one provider that have over hundreds of routers all over the world. So you don't expect them to run a single IGP domain across the whole world or across the whole internet. So there's a way they can break up the IGP domains based on different regions. Uh, of course, there's a better method that is used these days, which is the unified MPLS, whereby if you are using OSPF, you have different OSPF areas within the large MPLS network. But of course, confederations can also be very useful in splitting your large IGP domains in large scale environment. BGP domains can also be assigned to separate teams per region. That's also an advantage. So if this region is south south or southwest, you have your IT teams that are fully focused in managing and scaling the network within these regions. So there's this separation of duties within the network. So moving forward, you are going to see that preferred for devices with low memory and CPU. Yes, so that's also another advantages. So because all the routers within the subdomains only need to pair with each other here, so that in the case is fine for routers with low memory and CPU utilization. But of course, most of the boxes we have today has huge memory, 4 gig, 8 gig memory for processing BGP routes. So that is really not a major concern in today's network, because typically your A9 keys and your A1 keys comes with huge memories to hold the BGP table. So it's really not a major design. Now there are design disadvantages of confederations. Much of the disadvantages has to do with, like I said, it's much more harder to implement as compared to route reflectors. But I think it's easier, more easier to implement than the BGP full mesh. Uh, it is harder to partition the routing information if in this case where you are separating the IGPs. IGP rules still applies within the subdomains, so that is one of the for me personally, that's what I hate the most. In that within this subdomain, you do still need to have what we call full mesh. So by the time this subdomain starts to grow, they start coming back to the same issues that we are trying to run away from, right? So large sub AS still require full mesh pairing or route reflectors. So you see that within confederation, you can still have full mesh and what route reflectors designs within your sub AS, which I don't know. For me, it's not cool. All right. So the next thing we're going to talk about now is the BGP attributes. BGP attributes are more like the properties of or characteristics of routes. So if router A advertises prefixes to router B, those prefixes advertised are going to have certain properties or characteristics. So those characteristics of a route are what we call the BGP attributes. So those characteristics of a route has to do with the information such as the destination metric, the next stop address for those prefixes. Those are what we call the BGP attributes. Now, BGP attributes are what make BGP what it is. That's what makes BGP very flexible and the protocol of the internet. Like we said in the beginning, that the ability to apply multiple attributes to 3G route is what makes it a path vector protocol, and it's what makes it powerful and widely used, or that's what makes it the routing protocol of the internet. Now, when it comes to BGP attributes, you have different categories. You have the what we call the well-known mandatory attribute. We also have what we call the well-known discretionary attribute. We also have the optional transitive attribute and the optional non-transitive attribute. Now, when we talk about well known. Well known means that it is supported by BGP, that it must be supported by all BGP implementation. Things like your next stop. Okay. So when I advertise a prefix to you, I must specify what the next stop is, right? Okay. Optional means it must not be supported. It is optional attribute, but of course, when known means it must be supported. We also have what we call the mandatory attribute, which means it must be included in every BGP update that is shared. I also have what we call the discretionary attribute, which means it may or may not be included in a BGP update. Now, talking more about these attributes, uh, we also have the transitive attributes and the non-transitive attributes. Transitive means uh, PGP process should accept the update, uh, even if it's supported or it's not supported. And it also means that it can be passed on from one peer to the other. Example is the community attribute, because if I originate a prefix and then set a community attribute, then that attribute can be passed along to other BGP peers within your environment. For the non-transitive attribute, it means they are local to the device, attributes that are not supported by the BGP process, and hence they can be ignored. They are not advertised to peers. So transitive means I originate a route, I just set certain attributes of that route. Those attributes are carried along as we advertise those prefix to other neighbors. But for attributes that are non-transitive, it means those attributes are only local to your device, and so it's not be passed on from one peer to the other. For example, you are going to find out that attributes like weight is local to the device, and so it's not being advertised to neighbor. Attribute like melt, attribute like local preference. You're going to see local preference can be advertised to your IBGP neighbors, but it's not being advertised to your EBGP neighbors. Now, for the well-known mandatory attributes, one of them is the origin code. Origin has to do with is it being locally originated, or was it did you learn it from another IBGP pair, or was it redistributed? So, or what did you learn it from an EBGP pair? So you are going to find out that for locally originated prefixes, uh, prefixes learned from an IGP, it will be preferred over a prefixes learned from EGP and the others. We also talk about the next stop. So if I advertise a prefix to you, it must include the next stop information. Okay, the next stop information is what IGP will request to get to that prefix. So I can advertise a prefix to you and then tell you that the next stop is not me, but it's to my upstream peer. So you now have to use an IGP to request to that next stop. So the next stop has to be there and it has to be valid for you to have reachability. Otherwise, you have what we call you are learning the prefix, but to get to that prefix, you see BGP saying that that route is inaccessible. AS path information, of course, is used for loop prevention for EBGP peering. The idea is if I send you a route, I'm going to include in it my AS path information. So the idea is if it happens there's a loop in the internet, and then I end up getting back that route or those packets, I'm going to look at the AS path list, and if I see that my AS number is on it, then I'm going to reject that route. It tells me that there's a loop, and so I'm going to discard that prefix. We also have the well-known discretionary attribute, which is the local preference. You are going to find out that for local preference, higher local preference is preferred. So if I learn some route from a router A, I can assign a higher local preference to that route. Or if I have multiple paths, let's say I have multiple paths to a particular destination and I'm learning it from two neighbors. So if I learn it from router A, then I can set the local preference to be higher so that that path will be preferred. We also have atomic aggregate. Atomic aggregate has to do with summarization. You're going to find out that summarized routes are less preferred as compared to specific prefix. So if I do a summarization or I do an aggregation of prefixes and I then advertise it to my neighbors, you are going to see that uh, they are going to be less preferred as compared to specific attributes. So the atomic aggregate is a well-known discretionary attribute and means uh, it doesn't have to be included in all your BGP updates. So we also have the optional transitive attributes. We say that being optional means it must not be supported by all BGP implementation, but transitive means it can be passed along to other BGP peers. So like your aggregators, your communities and extended communities, these are transitive attributes. Communities are used a lot within a service provider environment. They are used for route tagging and they are also used for traffic engineering. They are used to create what we call filters on the internet. That is, if I learn some prefixes, let's say from Google, I don't want to maybe advertise those prefixes to another provider. So what I'm going to do is that once I learn those prefixes, I'm going to tag them with what we call a community value. And then I will create a route policy and say, once you see prefixes that has this community value, I want you to go ahead and deny them. Don't advertise them to my upstream peer. We also have extended communities, your route import and your route target. We are going to talk about this later when we are looking at the multi-protocol BGP implementations, especially for L3 and L2 VPNs. We are going to see extended communities are used to import and export routes from uh, from your customers into your MPLS environment, and you're also using it to get to remote destinations. Extended communities are transitive attributes. Then we also have the optional non-transitive attributes, things like your MEND, your originator ID, your cluster list, your multi-protocol reachability NLRI, your multi-protocol unreachable NLRI. These are all non-transitive attributes. MEND stands for the multi-exit discriminator or metric. Its use is not and higher metrics are always preferred, and it's always used only when you are learning prefixes or you have multi-path to uh, a destination that has the same autonomous system. So if I have two paths to my upstream provider, then I can use MERGE to determine which path will be my best path. We also have the originator ID. Originator ID has to do with is used mostly within the Route-Reflector environment. You want to see who originated these prefixes. You also have your cluster list. Cluster list has to do with your Route-Reflector, your cluster IP address. All those are attributes that are non-transitive and must not be included in all BGP updates. Now we should talk about the BGP best path selection process. Again, we are going to come back to all these and discuss them in details. First on the list is weight. Weight is a Cisco proprietary uh, attribute, so it's only known by Cisco, uh, and it is local to the device. So in best path selection, higher weight is always going to be preferred. Then if the weights are the same, then we are going to look at the local preference. Higher local preference are always also preferred. So if the local preference are also the same between your different parts, then you're also going to start looking at who originated the prefix. So if I originated the prefix, then it's going to be more preferred. So locally originated routes are much more preferred. You're going to see that when you originate a route, it's going to automatically be assigned at a weight of 32768. Shorter AS path. So uh, if the route were all locally originated, then we're also going to look at the path that has the shortest AS path. So if I learn a route from, let's say, an upstream provider, and then I'm learning those prefixes from multiple points, I'm going to look at the AS path information, and the path that has the shortest path will always be preferred over the logger path. We also have the origin code. So with origin code, we are looking at are you learning it through IGP or are you learning it through AGP or are you learning it as incomplete? So with origin code, we have your IGP, you have your EGP, you have your origin code of incomplete. You are going to find out that each time you do a redistribution within BGP, uh, you're going to see BGP is going to complain that it doesn't have enough information about that prefix, so it's going to tag it as incomplete. We are going to find out that IGP is always preferred over EGP, and EGP is most preferred over the incomplete route. We're also going to talk about the lowest MENT. If the origin code are the same, they will also look at, they're going to compare the MENT. MENT values are only compared if you are learning them from the same year. So like I said earlier, if I have a multi-part to the same provider, it means I can now compare the metrics between those two parts and then choose which will be the same. So now, if the MENT values are the same, then we'll continue to go down. We start to look at external IGPs are always going to be preferred over internal BGP routes. So the idea is if I learn a route from an external route, I'm always going to prefer it over what I'm learning from my internal peer. Okay, so the idea is when you learn a route from an external peer, the idea is this: it means we'll talk about this later as we progress in the discussion. We also have the lowest IGP cost to the next stop. Uh, so if I have a next stop, if when you advertise me a route and you say this is your next stop, what is uh, my lowest IGP cost in terms of IGP to that next stop? That is also going to count in BGP first part selection process. BGP multi-path is enabled with maximum path statement. Install all equal cost routes in the local RIP. So when you have multiple paths to a particular destination, then you can then go ahead and install all the equal routes in the local RIP. There are other tiebreakers, like the oldest route. So which route is the oldest route? Which route has the lowest router ID? Which has the minimum cluster list length? Which route has the lowest neighbor address? So by the time you BGP goes through this best path selection process, is going to figure out which path is going to be preferred based on this best path selection process. So for weight, if the weight are the same, it's going to come down to local preference. If the local preference are the same, it's going to look at the which is local, this was locally originated or it was learned from another IBGP pair. If that is the same too, it's going to look at the shortest AS path. If they are the same, we're going to look at origin code, lowest MER. It's going to come down to when you have the tiebreaker, you start looking at okay, which route is the oldest route, which route has the lowest router ID, which route has the minimum cluster list length, and which route has the lowest neighbor address. Now, going further with this BGP best path selection, just like I said, the weight is proprietary to Cisco as a Cisco specific parameter. It is local to the router. It is not being advertised to IBGP pairs. So if I'm connected to a router and I'm learning it through a particular path, I don't get to know why that router decides to use that path, because if he's using weight as his attribute for best path, then those attributes is not be advertised to your IGP pairs. You are going to say that routes that are locally originated are automatically assign the weight of 32768. Similarly, for the local preference, default value is 100. So if you don't set local preference, the default value for local preference is going to be 100. Their higher local preference is always going to be preferred. So if I have two parts A and B, if I set uh, the maybe the first part local preference to be A to be higher, maybe 150, and the other part is 100. The part that you are learning those preferences would of course be much more preferred. What I'm trying to say is this. Let me bring out my pen. So the idea is this: if let's say for example I have a router here, and then I let's say I also have another router here and this router. So let's say this router has a prefix that is being advertised. Okay, so this prefix is being advertised to this PS. So let me describe it. So this is my router 1, this is router 2, and this is router 3, this is router 4. So the question is, how does router 4 get to this prefix X? Okay, it has two paths, right? You can decide to go through this path, you can also decide to go through this path. Now, one way we can influence which part is it will be preferred is, one, we can set the weight. That's what we are talking about here now. So if I set the weight on this part to be higher, it means router 4 is going to be preferring this path to that destination X, right? So same apply for local preference. If I want to prefer this path as with to get to that X, then I'm going to be setting this. So any prefix I learn inbound along this path, then I'm going to set the local preference for those prefixes to be maybe something higher than 100, maybe 150. So it therefore means that this path will be preferred to that destination. But as it is, if I set here as weight of maybe 32768 and I set here my local preference as maybe 150, looking at the BGP best path selection process and which one is much more preferred, you are going to see that for Cisco devices, it's going to prefer the weight because weight is higher in the hierarchy. So higher weights are always going to be preferred. So even if the local preference here is higher, the weight value is going to be preferred. So we are going to see that for you to influence your outbound traffic. That is, if you want to influence how traffic are routed out of your network, we are going to use it. We are going to use what we are going to apply a policy inbound. Okay, so that's the point I'm trying to make here. That for you to, if I learn prefixes from router 3, I'm going to I'm going to tag them, or I'm going to set their local preference value to be higher, and I'm going to apply it inbound into router 4. So if I'm trying to influence how traffic route out of my AS or out of my network, then I'm going to apply the policy inbound. But if I'm trying to affect how traffic route into my autonomous system, then I'm going to apply policies outbound. We're going to talk about things like AS path prepending. We're going to talk about things like local preference, things like weight, how we can actually use it for traffic engineering. Okay, so moving forward here, we also have the origin code. I already told you that locally originated routes are always preferred. Uh, when you are originating a prefix, we earlier did it. We use the network statement. You are going to see that network when you use the network statement is actually going to be most preferred as compared to using either the aggregates or you are using the redistributor command. You are going to see that when you use the network statement is most preferred, but when you use redistribution is going to be second most preferred as compared to using summary route using with aggregation. So using aggregation, that's going to be least preferred. We also talk about the AS part. We also said that shorter AS part are always preferred. AS part can be ignored. We can use the command BGP AS part, BGP best part AS part ignore. When you use that command, you are going to say don't look at the shortest AS part. Simply ignore that. We are going to see that with BGP aggregations, I don't want to get too deep into all this. We are going to say that for confederations, that confed sequence and confed AS set are not included when it comes to AS part uh, information. The idea is within a confed, whether you are having different autonomous systems, so within your confederation, those sub AS are not does not count as part of the AS part information. The difference between a config sequence and also confess set is that for AS confess set is just another list of your sub AS, while the confess sequence has to do with another list of your AS part information within the confederation. And we are going to see that these parts are not actually included in the AS part information when you are looking at making your best part selection when it comes to AS numbers. Moving forward, we also talk about the origin type. We have earlier mentioned that for the origin type code, IGP is most preferred, followed by EGP, and followed by incomplete. So with redistribution, that's when you usually see incomplete. So you're learning the prefix and it's telling you that the origin code is incomplete. It means it was redistributed. For the med value, med is very complicated. It's only compared if you have multi-part from the same autonomous system. Lowest med are always preferred. So the med is actually a function of your internal IGP, right? So if I have a lower metric to a destination, that will always be preferred over the higher med value. But you are going to see that for med is actually used to affect your uh, outbound or how traffic comes into your network. So MED will be used when you are trying to affect how traffic route into your autonomous system. So one thing you are going to find out that it's very easy for you to specify how traffic route out of your autonomous system or out of your network, but you don't ultimately have control of how traffic comes in into your network. You are going to find out that if you want to affect how traffic routes into your autonomous system, then you are going to have to apply a policy outbound. But however, if you want to affect how traffic route out of your autonomous system, then you are going to apply a policy inbound. So inbound for outbound traffic, while outbound for inbound traffic. So for MED is used and is applied outbound to your neighbor to affect your inbound traffic. We also talk about EB. You're going to see that EBGP is always preferred over IGP. Uh, so if I'm learning a preface from an EGP, it's always going to be preferred over an IGP. So because if I learn a preface from an IGP, means I don't own that route, right? So what my concern is, how do I route to that destination? So I would rather want to route directly to my external neighbor than to route internally to another external neighbor. All right. So the idea is this: with EGP is, let me bring out my pen. If let's say I have a peer here, so let's say I also have my EGP peers here, right? Okay, so this is my autonomous system. Okay, and let's say I'm learning a certain prefixes on the internet. Okay, so let's say there's also another EGP peer here. All right, so and they have connection to this prefix X. So the idea is this: within your AS, what do you have? You have IBGP, right? So when you are learning a prefix, let's say you learn this prefix from this this your EBGP pair. Okay, let's say this router now. So let's say this is router one, router two, router three. So let's say this is another EBGP pair. So let E1, let's call this E2. So the idea is this: when I learn about this X, this prefix X from an EBGP pair, and I learn the same prefix from an IBGP pair, which part is router one going to be preferred? Which part will router one prefer? Now the idea is, you learning the prefix from an EBGP automatically tells you that you don't own that route, right? So that route is not wasn't originated from your autonomous system. So the idea is, would you want to go through your internal autonomous system to go out of your autonomous system to that destination, or just want to immediately route out of your autonomous system? I think they call it cold potato routing. Cold potato. If you read the TCP/IP Volume 2, there's also a term called the hot potato routing. Okay, in this case you always want to do what we call a hot potato routing, because rather than routing through your internal IGPs, you always want to route directly through an external IGP, because you already know that you don't own that route. So your what your concern is, how do you immediately route out of your AS, because the prefix you are learning is not within your autonomous system. If it was within your autonomous system, you won't even be learning it through BGP. What will you be learning it? You'll be learning it within as an IGP route. So long you are learning it from EGP, so EGP will always be preferred over what? IGP. So that's the idea of EGP over IGP route. Okay. So moving forward, we also talk about the tiebreakers. So when you compare all these different attributes and there is no match, then you start coming into the tiebreakers, like which route is the oldest route. So if I learned it through ISP A and also ISP B, which one did I learn first? So the oldest route are also going to win. We also have the lowest router ID. So which of my neighbor has the lowest router ID, which one has the minimum cluster list, and which one has the lowest neighbor address. Of course, this uh, what we have discussed, of course, is rather very complex, but you are going to see that as we start to apply this attribute, as we start to do the implementation of your IBGP pairs, You are going to see how they actually works. You are going to see uh, why they are so useful, and you are going to come to understand it better, these different BGP attributes. So in the next section of the video, we are going to talk about the actual implementation of the BGP full mesh designs. We are going to then we'll now come to talk about we'll come back again to talk about the different advantages and disadvantages of running full mesh topology, likewise the route reflectors and the confederation. Thank you. See you in the next video.